Welcome to this section of the course, which is all about the concepts involved in deep learning. The idea of this section is that we're not going to cover a lot of math. We're not going to cover a lot of Python coding or implementational details. Instead, I want to give you a kind of high-level overview, like the bird's eye view of deep learning models, what they are, what they look like, how they learn, and so on. And that's going to help you understand all of the later material in the course. So in this specific video, you are going to learn the conceptual idea behind artificial neural networks, which are often abbreviated ANN, and deep learning. So basically, an artificial neural network, or an ANN, it's like a way to transform an input into an output. So how does this transformation work? Well, there's some mystery in here. I mean, to be clear, I'm going to teach you everything that happens inside this box. It's a few equations, not really that complicated, but there still is a bit of a mystery about how exactly this works. Anyway, let me give you a few examples to make this input-output transformation a bit more concrete. So there are some algorithms that examine your web browser history to try to make predictions about the kinds of advertisements or videos or other sites that you are likely to click on. So the input is your browser history, the output is the probability of clicking through some link, and there's some fancy algorithm here in the middle that is doing this transformation. Another example is credit card fraud. So given some pattern of credit card transaction data, like the amount of the charge, the time, and the location, take those data and predict whether that transaction was likely to be you using it or whether there was a fraud being committed, whether someone stole your credit card. Again, we can have an ANN inside this box here making this transformation, making this decision about whether this was likely to be a credit card fraud. Another example is given your personal medical history and diagnostic test outcomes, we can have an ANN that predicts whether you might have a particular disease. Self-driving cars have cameras, and given the pixel values in the image, a deep learning model needs to determine whether there is a pedestrian about to walk in front of your car. Okay, here's one more example. Imagine that we have some text that was written in Malay, and we want to translate it into French. So then we can use a deep learning model that does language translation automatically. So you can see in these examples that they're all really different from each other, and yet the fundamental mathematical and computational bases of the algorithms inside this little mystery box here are basically all the same. And is this really magical? Is this really mysterious? Maybe it's just so inconceivably complex that only a mathematical genius can possibly understand what's going on here. Well, that's actually a difficult question to answer. Now, on the one hand, all of the math inside this mystery box, this input-output transformation, and I mean really literally all of the math, is very simple. In fact, most of the math is basic arithmetic. And then, there's a little bit of calculus going on here, but if you have high school level mathematics, you can learn all the math that happens inside here. But there are lots and lots and lots of simple pieces that are all put together. So the result ends up being quite complex. So is this thing really an incomprehensible black box? Well, yeah, that's a difficult question to answer, and it really depends on your perspective. You can ask different people this same question and get very different answers. So I guess my answer is that the math in the box is easy to understand, but the way that this thing actually works is much more difficult to understand. Now, this is an important topic of discussion, and we will come back to it periodically throughout this course. Let's go through a few more examples, but with a couple of visualizations. So imagine we want to predict whether a student will pass an exam based on how many hours they've studied and how many hours they've slept. So we have these two features, two dimensions, and we can visualize these data. And here's what the data would look like. So each dot is a student. The x-axis corresponds to the number of hours that the student studied for the exam, and the y-axis corresponds to how many hours they slept the night before the exam. And so the dots are red if the student failed and blue if they passed. These are all fake data, by the way. I just made up these numbers here for the visualization for this example. So what we want is an algorithm that can separate the red dots from the blue dots. Well, I think the solution is pretty obvious in this case. All we have to do is draw a line here. And then we predict that any student that has this combination of hours studied and hours slept, so a combination, a weighted combination of these two variables that gets the student below this line, below and to the left of this yellow line, we predict that that student will fail the exam. And if a student is up here, then we predict that the student will pass. Now you can see that this linear solution, this is a linear solution because we're drawing a line. This linear solution isn't perfect. It's not exactly getting every single student prediction correct, but it is quite good overall. Now, if this were a statistics or a machine learning course, you would learn that we can solve this problem using, for example, a logistic regression or perhaps a support vector machine. But here in a deep learning course, we are going to solve this kind of problem using artificial neural networks. So we might use a graphical representation of the network to indicate that we have two inputs into the networks. That would be the hours slept and hours studied. This extra term here, which is called a bias, and then we compute a linear weighted sum of these input features, apply a nonlinear activation function like a sigmoid, and then get our output of the model, which in this case is a prediction about whether the student will pass or fail. Now, don't worry if this looks complicated or weird or incomprehensible. I promise you are going to understand exactly what all of this stuff means pretty soon in the course. Here is a different example. Let's say that our goal is to separate the yellow squares from the blue dots. Now, this is a trickier problem because it's not possible to draw a straight line like in the previous example. In other words, there is no linear solution to this problem. So we need a non-linear solution. And this is where deep learning really excels. This is where deep learning really shines through. Deep learning is amazing at solving complicated problems that require non-linear solutions. Well, you can imagine that in this case, the separating line is actually a separating circle. Again, if this were a statistics course, we could still come up with ways to solve this problem, but you would need to know a priori that the best discriminator would be a circle. And with deep learning, you don't need to know anything about the nature of the correct solution. The deep learning model will automatically figure out that something like a circle is a good solution. Okay, now I want to tell you a little bit about the math of deep learning. Well, this is not all of the math of deep learning, but actually a surprising amount of the math of deep learning is really, really simple. So we say that our prediction of the world, which is the output of the deep learning model, let's call that y hat, this little character, this little caret symbol on top is often called a hat. So y hat equals x1 times w1 plus x2 times w2. So y hat is the prediction about the world. This is what the model thinks is happening in the real world. For example, whether the student will pass or fail, whether a picture contains a pedestrian walking across the street, whether the credit card transaction is fraudulent, and so on. The x's are the data. Now here I'm only showing two data values, but of course in practice you have lots of data values, maybe dozens or thousands or millions of data values. And these w's here, these are called the weights. These are the numbers that tell the model how important each of these data features is for the prediction, for the model output. Now, we don't actually specify these W's. They are learned by the model through this amazing procedure called backpropagation. So we can think back to our example of passing or failing an exam. Let's imagine that variable x2 was the number of grapefruits that the student ate in December 2 years ago. Well, that's a weird variable to include in the model, and it's unlikely to be relevant for predicting whether someone will pass an exam tomorrow. So the deep learning model will learn that this variable is not predictive, and therefore the model will learn to set this weight value to 0. Okay, now this equation here is linear. It has multiplications and sum, which is the definition of a linear model. So a model that looks like this, that has this equation, can solve linear problems, but not nonlinear problems. So therefore, in deep learning, we add a nonlinear function to this linear expression. So we take the linear part of this equation and we pass it through some nonlinear function, which is what this sigma here represents. Now, this nonlinear function is usually something really simple. In fact, it turns out that the simpler nonlinear functions tend to work better than complicated nonlinear functions. So here I'm showing an example with a log function. This is just an example. This is not just to try to make this more concrete. In fact, we often use even simpler nonlinear functions than the logarithm. Okay, now this one equation here is neat, but this is not very powerful on its own. So what we do in deep learning is treat this thing as an elementary building block. It's like a brick. And then we build an entire complicated world-class structure by putting a lot of these simple bricks together. And then we can visually represent that using a diagram that would look something like this. Now, each of these circles here, each of these units, these are sometimes called artificial neurons, although I actually strongly dislike that term for reasons that I will explain in a later video. But anyway, each of these units actually represents the simple equation that I showed in the previous slide. Now here I'm using a slightly different notation just to make it more compact and also more general, but this expression really is just the linear weighted combination plus the nonlinearity. And the key is that we repeat this simple computational building block many, many, many times. Now, obviously, there is more to know about deep learning than just this one slide, but this really is the elementary procedure. This really is the idea of deep learning. So, in general, the deep learning model is a transformation from some input data into an output prediction about the real world. There are different families or different ways of optimizing deep learning models for different kinds of problems. If you have a data table, and you want to predict an outcome, then you're probably going to use an ANN architecture like what I illustrated in the previous slide. If you have a picture and you want to know whether there is a cat in the picture, then you're going to use something called a CNN or convolutional neural network. If you have a time series like an audio clip and you want to see if you can predict some specific outcome, then you would use an RNN, which stands for recurrent neural network. And I already gave another example of translating text from one language into another that's also done using an RNN architecture. So very different kinds of problems and different terms, different model architectures, but the underlying mathematical and computational principles are all the same. Furthermore, deep learning models can be visualized in a variety of ways. So different visual representations are used to illustrate the same concepts. But don't be concerned and don't be intimidated. These different deep learning models are actually all really similar to each other. In fact, they are much more similar than they are distinct. So don't be intimidated by the diversity of terms and graphical representations of deep learning architectures. By analogy, here's an analogy. Different kinds of buildings may look very different from each other, and different kinds of buildings are suited for different purposes, but the electricity, the plumbing, the windows, the ventilation systems, the physics that govern the structural intensity, that's all exactly the same in all these different kinds of buildings. Okay, so in this video, I provided a big picture overview of different kinds of deep learning models, and I also explained a bit of the math underlying deep learning. The main point was to show you that although there is a lot to learn about deep learning, it's not quite as much as you might think. Now, before getting into the details of how deep learning models work mathematically and how they are implemented in PyTorch, I want to give you some more high-level conceptual understanding of deep learning models, and that's coming up in the next video.